Hi everyone, my name is Matthew Poncini, and today I'll be presenting extracting training data from large language models. This is a look into how powerful models like GPT-2 can unintentionally memorize and regurgitate training data, including private information. This paper was published in June 2021, and the findings remain highly relevant as models continue to grow in size. All right, so large language models are trained on massive data sets and learn how to predict the next word in a sequence. But what happens when they start outputting exact memorized sequences from their training data, especially if that data includes personal or sensitive information? So, this research demonstrates that even without direct access to a model's training data or parameters, it's possible to extract training examples just by prompting the model in the right way. All right, so leakage is often linked to overfitting. So, when a model performs well on training data but poorly on unseen data. So, overfitting can indicate that the model has memorized specific examples from its training set rather than generalizing. For frequent sequences, the model can learn general patterns, but for rare sequences, it can just memorize the entire string. When a model sees the same rare example repeatedly, or if it's trying to minimize loss on low frequency string, it can just memorize the exact output. Over parameterized models, those with lots of weights, are especially capable of memorization, but the key point is that memorization can still occur even when there's no overfitting. So that's the crux of this paper. Memorization happens in state of the art models. So even when the train and test losses look nearly identical, you can still find memorized samples in the output. That means that traditional metrics like loss or accuracy don't fully reveal privacy leaks. All right, the paper uses OpenAI's GPT-2 models at three different scales. They use base model, we'll call it the large model GPT-2 that has 1.5 billion parameters, medium GPT-2, and small GPT-2, and they only use black box access. Um, so, although the training data for GPT-2 is fully public, um, they they never looked inside the model. They just prompted it and observed what it generated. All right, two key definitions for us: model knowledge extraction. If a string can be generated by the model with high probability given a prompt, it's considered extractable. And k-IDICT memorization. If a string appears in at most k training examples, but is extractable, it's k-eidetic memorized. And so it's the lower the K, the more serious the privacy concern. But if we don't have access to the training data, how do we know the size of K? So one way to do that is through perplexity. So one way to spot memorization is by computing perplexity, a measure of how surprised the model is by a sequence. Very low perplexity often indicates that the model is highly confident, potentially because it memorized the sequence. All right, so a breakdown of how this paper extracts training data. Um, so again, they only use the black box language model access. And their methodology involved generating 200,000 samples for each of the three prompting strategies. So they use empty prompts plus top end sampling, uh, temperature decay sampling that's also using empty prompts, and then they also use internet derived prompts. They applied filters like perplexity, model size ratios, zlib, and we'll go into detail on how they filter through the data sets in a moment. But they, um, once they filter through the data, they manually reviewed each sample to determine whether the model was um, memorized or not. All right, so this diagram summarizes the methodology used to extract memorized training data from large language models such as GPT-2. So the process starts with generating 200,000 text samples from the model using the different prefixes as described in the last slide. These prefixes can be empty, synthetic, or scraped from the internet to mimic realistic inputs. Once the samples are generated, they're scored and sorted using one of the 6 ranking metrics, such as perplexity, zlib, compression ratio, or cross model comparisons. Um, since the language models can generate repeated outputs, there is a deduplicate step. So the team filters out exact or near duplicates to ensure diversity of the samples. From there, they selected the top 100 samples based on the metric being evaluated. Finally, they manually verified whether each sample matches content found on the internet. If it did, and that content wasn't in the model's known training set, it's flagged as memorized. All right, so here's a little bit more detail on the prompting methods. So for top N sampling, they generate text from a blank prompt, and then for each next token, they select from the each next token is selected by taking randomly selecting the 40 next likely tokens. Um, they use temperature decay, so similar as the top 40 sampling. However, they start with a high temperature to encourage exploration. Then it decays over the first 20 tokens to a temperature of 1 to reduce it to lock in into a likely sequence. Then they used internet prefix sampling. They used 10 or realistic 10 token sequences from Common Crawl, but they avoided GP2 training data, such as data from Reddit, to seed generation. Right, to detect memorization, they applied filters. So the first filter they did was just perplexity, as we chatted about before. This is how predictable the sequence is. And so if an output had a low perplexity, it was ranked, and that was a candidate for memorized content. We also did ratios to see if larger models memorized more. And so they compare the ratios between the smaller parameter GPT-2 with the large one, as well as the medium-sized one. And it shows how memorization scales with model size. All right, so zlib score. Zlib score tells us how hard text was to compress. Um, so low compressibility suggests memorization and structured content. Lowercase sensitivity and window-based perplexity were also used to catch subtle signals. So lowercase, if lowercasing the string makes perplexity go up a lot, then that could be an indicator that a string was memorized. And then the window filtering basically checks to see if substrings of the outputs were memorized, even though the full sequence may have not been memorized. If a substring was memorized, we wanted to include those in our samples as well. All right. So so they took 100 samples from each of those methodology and from 200,000 different data sets with the sampling techniques. And what that left was 1,800 samples from the 3 data sets of 200,000 generated samples. So for each of those 1,800 selected samples, one of the 4 authors manually determined whether the sample contained memorized text. So they identified 604. They identified 604 uniquely memorized training examples from the 1,800 possible candidates. So what the researchers found included license agreements, email addresses, usernames and passwords, and API keys, all of which are private and problematic to be available just by prompting an LLM. So, and then some strings were up to 50 to 100 tokens long and were reproduced word for word. All right, the paper breaks down the different categories of the 604 memorized samples. Um, we see that 46 of them were named individuals that came from non-new samples. And then 32 of those samples were contact info, which includes, address, email, and phone numbers. All right, and so they broke the results into categories and linked them back to the sampling strategy we use. Um, and I think what's notable and will serve as a reminder is that um, for top end and temperature prompts, those were empty prompts. And so even empty prompts produce memorized contents. So that's especially concerning. It means that attackers don't need to, be clever to extract data. So a key insight, as we can see, is that the largest number of memorized samples actually came from zlib filter, which again tells us how difficult it is for an output to be compressed. Um, so if the model found a string easy to generate and that string was hard to compress, then more often than not, that string was memorized. All right, so this matters. This research shows that training data extraction is practical, even with basic prompts, even with empty prompts. Attackers don't need internal model access. Prompting alone can leak data. And so that raises bigger questions, in AI safety, and how do we prevent this? Another key takeaway is that larger models memorize more data. The largest model memorized 18 times more content than the smallest model. As models get larger, this problem gets worse unless it's mitigated deliberately. So, with models becoming even larger today, this paper was published in 2021. It's likely that there will be more privacy leakage. And then, as we're going back to a previous slide, memorization does not require overfitting. Even though train and validation losses are close, individual examples can still have very low training loss, suggesting over memorization. So a small train test gap doesn't guarantee safety. All right, moving on to discussion questions. What practical steps can developers take to reduce the risk of memorization in large language models without compromising performance? Who should be responsible for enforcing these safety measures? All right. So The authors did tap into this question a little bit. They said that training with differential privacy, vetting the training data for sensitive content, limiting the impact on downstream applications, and auditing language models to test for memorization. All of these are interesting and promising avenues of future work, but each has weakness and are incomplete solutions to the problem. So um, I wouldn't say that there's any single fix. This is an area of active research, and um, this whole entire paper um, was, I think, the purpose of it was to make aware that it is possible to leak data, um, even with empty prompts. Um, and so I would say that that the developers are the ones that would be responsible um, for for making sure that the privacy data doesn't get leaked. All right, what practical steps can developers take to reduce the risk? Oh, same question. Um, yeah, I'd say deduplicating training data will lead to less memorization of that specific data. Um, and then applying filters to sensitive data, I think, is a very you know practical step. And then using a methodology similar to the one presented in this paper, or using checklist. You know language models should have post training audits ran to ensure that you know sensitive data isn't leaked. All right, and then why do large language models, which are better at most language tasks, actually memorize more rare examples from their training data? Does this mean we can't have both highly capable models and strong privacy protection? This was similar to um, the other question that was posted. The finding that larger models increase memorization risk seems counterintuitive. Why might increasing the number of parameters cause models to memorize particular examples rather than simply enhancing their general language understanding? Um, Say, like, in a nutshell, more parameters allow the models to fit more training data. So larger language models have a larger capacity, and it allows them to minimize loss a little bit better. Um, it kind of goes back to um, how capable is it for the language model to minimize loss. Um, and so if it does it that better, then what happens is that it leaks memorized data. Um, And so I think that's the unsatisfying answer to that question. The larger the language model is that the better it is um, at its job to minimize loss, and sometimes that results in memorized data being leaked out. Um, okay, that is my presentation. Um, it was very interesting to kind of read about the methodology. I think it raises a bigger question into um, it just raises concern on what steps should be taken to prevent um, you know a, attacks from users that are trying to get access to personal data for whatever means. I posted in the discussion a link to the GitHub that was used by the authors, and then I converted it to a Jupyter notebook friendly version of the code. So if you prefer to use that, then that is also in the discussion as well. All right. Thank you guys. Bye.